NeuroSPF is a tool for the symbolic analysis of neural networks. Given a trained neural network model, the tool extracts the architecture and model parameters and translates them into a Java representation, which can then be fed into Symbolic Pathfinder for symbolic execution. In this video, we show the application of NeuroSPF in generating adversarial inputs for an image class network trained on the MNIST dataset. The figure shows the overall framework for NeuroSPF. User inputs the class model into NeuroSPF. The translated component will generate 5 sets of files. The JSON file have critical information about the neural network, such as the dimension of the weights and biases files, number of layers, and type of layers in the neural network. Weights and biases files contains the weights and biases for each layer. Config file specifies the configuration settings for SPF. The last set of files is the Java code. User also has the option to run this Java code if they do not want to run SPF or symbolic execution. The weights and biases files are read using peer classes for efficient symbolic execution. Once read, these are input to the SPF along with the Java code and the config file. We first run the translated component. The class model is stored in the MNIST low-quality.h5 file. Argument model specifies the class model file to be translated. Output argument specifies the folder where the translated files will be generated. We specify the location of the Eclipse project. The argument D provides the user the option to run this demo example. Now the translator has generated a set of files. We can see that the summary of the trained translated neural network is available on the console. We now go to the Eclipse project to see the generated files. We first refresh the project so they are available in the Eclipse IDE. We run spf dnn.jpf file so that NeuroSPF can start generating adversarial inputs, and in the meanwhile, I will explain each of these files. The DNNT class implements the neural network. Each part of the code represents a layer in the neural network. For example, layer 7 represents a ReLU activation layer. Internal data file contains the arrays to store the weights and biases for each layer of the neural network. We have a dnn.json file which describes the architecture of the neural network. Then comes the spf dnn.jpf file. This specifies the configuration settings for SPF. For example, line 4 specifies that the minimum value of the symbolic variable should be 0 and the maximum value can be 255. The constraint solver to be used is specified to be Z3. Now comes the symbolic driver.java file. We first read the input image, which is stored in the demo image file. The image is read. The image consists of 784 pixels and is represented using an array, 2D array of size 28 by 28. We make the pixel 15, 15 symbolic using the annotation debug.addSymbolic double. Once this variable has been made symbolic, we read the biases and weights file using the peer classes in SPF. We also add an assertion that the NeuroSPF should return a value for which the neural network predicts a label other than 8 because we are generating adversarial inputs for an image for whose original label was 8. We used annotation debug.getSolvedPC to get the constraints and solve them using Z3. Then there is another annotation debug.getSymbolicRealValue which will print the required solutions. We then print the total execution time. Now we go to the console output where we can see that the original value for the symbolic pixel was 0. But if we make that pixel value to be 218, we can get the neural network to classify that image to label 9 instead of label 8. And NeuroSPF was able to find this in just 43 seconds. The complete code is available at the GitHub link of the project, which is github.com/NeuroSPF/NeuroSPF. We believe that NeuroSPF will enable researchers to analyze neural networks. Thank you.